So we're going to move on into the next speaker, and we're lucky he's here. Okay, so Professor Greco, are you here?
Hello. Yes.
Brilliant. Okay, thank you very much for being here. 40 minutes ahead of the time, so thank you.
Okay.
You're saving my problem, saving me out of the trouble at the moment, because we have two speakers. One speaker would give a recorded message, another one we don't know yet.
Okay.
So I will be delighted to invite you to give the presentation if you upload your presentation, and I'm going to do an introduction of you. So Professor,
I'm sharing my screen. I think it's okay.
Yeah, it's coming.
Okay.
That's brilliant. Thank you. Okay.
Thank you.
So Professor Greco is a European AI Fellow, President of the Italian Association for Artificial Intelligence. He's also a Professor of Computer Science and Head of the Department of Mathematics and Computer Science, the University of
Calabria.
Okay, I need to say it the Italian way. Okay, so the floor is yours, Professor Greco. Thank you very much.
Okay. Thank you very much to you for the kind invitation. And I also send my greetings to everyone who is in this chat, and we'll see also my slides later. Well, I would like to present you some results of some of our recent research in a field which attracted me a lot in the past. Then for some times I decided to stop a bit, but nowadays I think that we still need more in the field of automatizing business process. So here I put some references, and this is an EJK paper, and I actually will discuss a bit more for material taken from a journal paper. So the talk is reasoning about business process in LTL. And I would like to discuss with you why these names, or what I really mean for reasoning about business process. Well, the point is the following. Every one of us knows that in real life we have some process which goes behind the organization, and this process typically are aimed to achieve some goal. And so, in order to achieve this goal, we have a number of actors that interact with each other. They typically collaborate in order to achieve this goal, and they have to take care of a set of resources. They can exploit these resources to execute some task. And actually, in order to integrate, cooperate, organize, and even orchestrate all these pieces, all these actors, all these resources, we typically would like to have a workflow. So workflow is, in our view, a kind of automation of all these tasks, of all these activities. And clearly enough, in a workflow automation, the crucial point is actually the method to specify the order in which the various activities have to be executed. So this is an important point. Even in this pictorial representation, you see here that there is a starting activity, a terminating activity, and then you won't typically ask question, okay, what's the next activity I have to execute? And then can these two activities be executed in parallel, and so on. So ideally, we would like to design a process by putting the actors, by putting the resources, the task, but the most important thing is the order in which the various activities have to be executed. Now, let's look at the tradition. The tradition of business process management says that we would like a procedural approach. So what we mean by a procedural approach? In a procedural approach, like, for instance, Petri nets. So this is something that most of you are reminiscent of Petri nets. You should know this is a very nice framework to describe parallel behaviors, but of course it's rather heavy because you have to explicitly define all possible behaviors. So assume that you have a kind of a scenario in which you have many different branches, many things that can go in parallel. You are forced to describe each of these tasks in parallel. You are forced to discuss the various branches and so on. So every single detail of your process has to be specified. So in theory, for a course, actually a university course is fine, But when you go in practice, look at this picture here below in the bottom right part of my slide. Here you can see that real life is much more complicated. These are so-called spaghetti-like process. So you have many different relationships of precedence, and so describing everything is typically very difficult. So in the last few years, there is a kind of interest, and that's why I'm attracted by these approaches, because these approaches essentially give a fresh view on declarative programming. So declarative programming had a big history, right? Played an important role in the development of artificial intelligence. And nowadays, people say, okay, but maybe the declarative programming style approach can be used to specify business process. Well, in this case, the idea is very simple. We use a kind of logic-based constraints. And these logic-based constraints have typically, so there are a number of languages, but they're typically very, very simple behaviors. For instance, like this line which connects to activity A and B, and then these are from B and C, and these are then transformed in very simple constraints. But the point of logic-based approach is very different from procedural approach. So in a declarative approach, everything is allowed. So the point is that you do not want to say, okay, the real life is like that you specified 10,000 of different ways of evolution of your process. You just say what is forbidden. So essentially you take the inverse approach. So rather than say, okay, everything is forbidden unless there is a path, you say, okay, everything is allowed. So please let the process evolve, but I put these constraints. And these constraints have typically a graphical form, and they are very nice to be built. So there has been an interesting paper which basically proposed this kind of approach and made a nice overview, which is a paper by a paper which introduced this concept of declarative workflows. So I built on top of these declarative workflows, and the idea is very simple. So just to understand the basic idea. So you have these graphical patterns, right? And these patterns are constraints. So if you do not put any pattern, so this means that everything is allowed. If you put a pattern maybe like this, then this is a pattern that says, well, whenever A is executed, then the next activity should be B. Or maybe this that says, okay, A and B cannot be never executed in the same process enactment. Well, how to specify the semantics? And now in this place, the logic comes into play, because these are graphical patterns, but the formal semantics for specifying what they really mean is given in terms of a temporal logic. And so this is the second part of my talk, LTL. So we use people, the research activity, the research community, nowadays is very, very interested in understanding whether linear temporal logic can be used to provide semantics and to reason about this process. So the idea is that after that we have a semantics, essentially reasoning about process is precisely the same as reasoning about LTL. So with my group, what we did in the very last few years, so we have a model, and this is his declarative model, in which these are just the constraints I told you. But the nice thing is that this is the high-level view, but there is a very formal semantics. Of course, you have not now to understand the semantics there, but what I want, the idea that I want to convey to you is that every constraint, for instance, this is a constraint, is translated in one block, which is a logical constraint with a precise semantics. So this is a large formula. So those of all of you, I assume, are familiar with Boolean formula. So the formula that we can build by using and, or, not, the Boolean connectives. Now this is a temporal logic because we have also temporal operators, which I'm going to introduce soon. And these are temporal operators allow us to reason about events in the past or in the future. And now this is an LTL encoding. And what's the nice thing is that we can reason about that. So we can ask a question related, okay, will this process will eventually find a deadlock? What's the best way to achieve this result? Is there a way that we use as few as actors as possible in order to achieve some goal? So we can do a lot of things by just using a reasoner for LTL. Well, of course, the reasoner for LTL produce an output, and the output is typically the possible models. So the possible models are a sequence of set of events. So here you see that we have essentially each model is a sequence of states, and each state is a set of activities. So these are the activities that are going to be executed in parallel. Okay, so for instance, here executing O, then maybe I say, okay, there is no order among the execution of M, T, C, then I'm going to execute S and finally E. Okay, that's it. So this is a kind of model, and we can have this model by using this kind of formulas. So what we can do with LTL, so why this is so appealing? Well, first of all, I must to say the following aspect. If you have a look at all these major AI venues, both in Europe and the US, you will see that no one basically is discussing about linear temporal logic, so the classical logic from the 60s and the 80s. Indeed, people are talking about linear temporal logic on finite traces. So what is the main difference? The main difference is that in classical logic, you assume that you have an infinite trace. And this is typical in logic, because in logic, we typically reason about infinite models. Well, but nowadays we are more pragmatic, we are more engineering, and we say, okay, this trace is at a certain point ends, and so we have finite traces. So the horizon is not fixed. So it is not that we say, okay, the process lasts 5 days. We say, okay, the process at a certain point will terminate. You do not know the horizon, but it makes a huge difference working on infinite things, you know, and working on finite things. So this is a real life setting, and this finite assumption is very crucial. So in the finite assumption, you can say, you can have temporal operators saying, okay, what will be tomorrow, the next activity? So you can ask you can define constraints saying something like, okay, if I execute an activity now, then the next, so tomorrow, the next time, I will execute this other activity. And you have the until, the release operator. Just I want to point out the weak next. Why the weak next is interesting? Because think at the last time point. In the last time point, when the horizon finishes, then you can say, okay, the next activity. So the next activity is true in the last time point, whether either you have really a next activity or you finish there at the end of the execution. Well, there are also shorthands, for instance, always. So always means what means every time. So in every time step, something must happen. Eventually, it means that at a certain point, some behavior should hold. Okay, we can deal with all this scenario, and so a process eventually can be recast, and we have automatical tools. We built a lot of these tools in which your process, the thing that phi is a process, is then translated into a formula. And then on this formula, you can basically identify the trace which satisfies it. So this is a proof that the trace made by A, B, AC, AA satisfies your formula. Okay, these are just to see you how this is satisfied. Okay, the interesting question. So if any of you by chance is interesting to work on this topic, well, there are 3 questions that typical researchers are going to address. The first question is very simple. Well, we know everything about linear temporal logic on the infinite world, which is not the real one. What about on the finite world? In particular, if a formula is satisfiable, is there any guarantee that a model has exponential length, linear length? So what about the length? So I define a process. Is there any bound on the length of the process that I should consider? Notice that this is a very crucial question, because if you have a process, let's say, with 10 activities, and you know that if there is if this process is well defined, then there is a trace, let's say, of 2 to the 10 activities, then you at least know that a brute force approach is at least do the job. So you can reason with a brute force approach. Well, what about the results? So this is I put all the results collected from the literature by myself. And the picture is the following. It depends on how you combine the temporal operators. So in general, there is the nice results, and these are results coming by the Giacomo and Vardi, and one results from the 80s. If you combine these results, then you realized that there is this exponential bound. So essentially, all these models are exponential bounded. And notice that in symbolic model checking, this is very important because typically most of these problems are undecidable, right? So the fact that there is an exponential bound is very nice. But we can, and then there are also how to prove that you need at least exponential, an exponential length. Well, there is a standard trick to encode an n-bit counter. So this is the proof fragments. But the nice thing is that there are a number of fragments in which you are guaranteed that if a model exists, it has a linear length. So it is very, very effective. So you can do reasoners which are very fast and very, very effective. So the gray area, from the practical point of view, is the tractability island. So it means that on this kind of green fragments, we can do things that work really in practice. Well, the second point is complexity. Well, I will not bother you with the complexity results, but it's something that people in symbolic reasoning take care of. And here, what we see is that the picture is very interesting. So the results are not symmetric. Well, negation-free, this is interesting. So there are a number of processes, a number of constraints in which you do not need the negation. So you don't want to say the activity is not executed. And so everything becomes very easy in absence of negation. And instead, here is another technical thing. If you want that there are no activities in parallel, then basically this is essentially the same of do not having these constraints. So in some cases, you do not want activity to be executed in parallel. And our result says, okay, reasoning on this kind of fragment is immaterial. It's the same of allowing things in concurrency. Well, what a nice thing. Among the various, the first thing is that you need a solver. And here I present to you a very simple idea. And the very simple idea is the following. Since now we know that the formula have a bound, then the nice trick that you can use is that you can take your process and you can encode reasoning over LTL in terms of reasoning over a SAT formula. So I think that you say, why we are using SAT formulas, SAT solvers? Well, because SAT solvers, you know, are very, very effective nowadays. So SAT solvers are completely far from the story of the SAT solvers of 10, 20 years ago. Now this is a very, very effective technology that can scale up to thousands of variables. And so it is very nice that we can translate this fragment in terms of a SAT solver. And this just shows behind the scene how the translation works. So of course you work on a parse tree, and then you have variables which says whether something holds or not in every timestamp. So there is the encoding is very simple. You can envision what the kind of encoding is. And these SAT solvers are very, very powerful. For instance, here I present to you some results on a very standard data set, and I want just to show you that approaches that do not use the SAT solver encodings typically are really outperformed by the SAT solvers approach. So in these are gray area, those in which the performances are definitively better, where more traditional essential automata-based approach works better in some cases, which are this red area, but you know the prominence of the grid areas and the prominence of the yellow areas, where more or less the traditional automata-based approach and the SAT solver approach are more or less comparable. And these are other results that you can find in the paper. But now this is not enough, I think. So what we were very interested in really the last few months, and we are actively working on it, is the weighted case. So we moved it from a very simple question. So the logics typically completely neglect quantitative properties. But you know, I want to use this in real life. And when I use this kind of approaches in projects, in real life projects, also with some big companies, they told me, yes, but what about probabilities? What about cost? Every activity has a cost for me. It is not the same if your reasoning tells me, okay, this is a path, but with a huge impossible cost. I would like to know the minimum cost. And so the real life pushes for a quantitative version. And we introduced a variant, and I want to discuss with you and then conclude my presentation with this variant, Well, in this variant, we just introduce a valuation structure, which is just 3 ingredients, very simple. So the first ingredient are the weights. So what we mean by weights? So every activity has a cost, or has a time, or has a number of resources, or has whatever you want, but has a real number associated, or even a vector or real numbers. So it is very flexible and it is natural. And then if you take a trace, so this is a trace with O and T, C, C, so in the classical world, then these are just a plain sequence of activities. But now you can say, okay, O is a cost, and so I take WO, its cost. C is a cost, and then take its cost, WC. And then for those activities which are those states which combine 2 or more activities, I just use an operator to combine the weights. So for instance, here is just the combination, finger plus. I just sum the weights, or maybe max, or whatever you have in mind. So essentially, every state now has a cost, and the cost of a trace is just the combination with another operator. So essentially, we have 2 operators, one which aggregates the weights at the level of the states, and the other that works at the level of the trace. And armed with this, so here you see, for instance, an instantiation where we have a plus and where we have star, so the times. And that's easy. And you can do a lot of things. For instance, in this case, I just want to mention that to do things more effective implementation, we also need to consider monotone function. So by monotone, we mean that weights have to be positive and with the properties which are very natural. So their combination is greater than the maximum. And so you can think about very interesting function. For instance, if you use plus plus, then maybe you interpret this as a cost. It means that you are looking for the minimum weighted cost execution. That's very nice, right? The minimum weighted cost. Well, maybe you can use plus max. In this case, you are going to consider the maximum number. Well, if your weight is the number of employees, then this can be the maximum number of employees at each step.
Professor,
so what does it mean?
Greco, yes? I would like you to conclude in 3 minutes.
Yeah, thank you very much. In fact, we have 3 minutes. So you have the maximum number of employees at each step. And finally, with max plus, we have the overall time, the parallel you assume the overall time with parallel execution at each step. Again, the 3 kind of results, you can have a number of complexity results, you can depict the picture. Again, it is interesting to characterize how to have a practical solver. In this case, we can use the minimum weighted path approach on the automata. And finally, of course, the last thing, the thing which I'm most interested in is that you need also practical solvers. And from the paper here, you have everything to download, the 2 solvers, one which is based on a breadth-first exploration and another which is based on a depth-first search. And you will find results which allows you to understand which one is the better in which and in which scenarios. The story is that there is definitely no better choice, and it depends on the kind of process you are dealing with. So this picture just says that we are basically able to reason with all the formulas taken from standard benchmarks in the literature. And so as promised, that's it. Thank you very much.
Thank you very much. So if anybody have any question to ask Professor Greco, please put it into the chat. And if you can leave your email address there as well, Professor Greco. Yeah. Sure. I always think of it's really important to have engineers, scientists, and business people working together, because the world becomes so complicated. The complex problem need people to work together. And your presentation on business model and how to optimize them using AI is just really very, very timely. Thank you very much for that.
Welcome.
So